Welcome back, Focus Learners. I am absolutely thrilled to have you here for today's explainer. We're looking at a blueprint dated July 16, 2026 from Luis Manuel Ortiz and Ostraza, and let me tell you, it outlines a literally mind-bending leap in computing technology. We're talking about a complete paradigm shift here, moving away from traditional electronics and diving straight into the realm of light-driven intelligence. It's called the Ortiz Photonic Fractal Core, and it completely reimagines how our devices process the world around us.
Okay, let's dive into this, because this quote is the absolute bedrock of today's topic. This is not a normal computer chip. The source material hits us with this provocative statement right out of the gate, and it really shakes up our usual understanding of hardware. We aren't just looking at a slightly faster silicon processor. No way. We're looking at an entirely unprecedented modular system upgrade that completely abandons ordinary digital instructions.
So, here is our roadmap for today. First, beyond the normal chip. Second, the light logic sandwich. Third, decoding the massive numbers. Fourth, real-world capabilities. And finally, a new physical intelligence.
Let's get started with Section 1, Beyond the Normal Chip, a new system upgrade.
For decades, traditional silicon chips have faced some pretty hard physical limitations. We're talking heat buildup, sequential processing bottlenecks, and just this strict reliance on software to tell passive hardware what to do. Well, the Ortiz core is presented as the ultimate solution to these exact issues. Let's break down what this actually is. Imagine a removable, modular unit that sits perfectly inside your phone or laptop, but instead of just executing fixed instructions, it acts as a parallel reasoning layer. When you feed it information, it literally converts that incoming data into light. It then organizes that light using pure geometry and material structure to compute and self-correct on the fly. It's wild.
To really wrap our heads around this, let's compare the two approaches. A normal digital chip processes sequentially, right? Step 1, then step 2. Think of it kind of like a car navigating a fixed maze. It has to follow the walls, hit dead ends, turn all the way around, and try again. The photonic fractal core, on the other hand, relies on parallel light processing and structural reasoning. In our analogy, this core is a maze that physically reshapes itself instantly to create a direct path for the car the exact moment it enters.
Moving on to Section 2, the light logic sandwich, anatomy of a breakthrough.
Now, what's really interesting here is how this exact 7-layer sandwich stack is actually engineered. Every single layer has a very specific job in manipulating light and noise. You've got this flower of life diamond skin on top, handling structure and routing. Right beneath that, graphene and flash graphene provide incredibly fast optical control, and they do it with super low energy costs. Then, slate and mica step in as barriers to filter out the noise. Right in the middle, the fractal expansion layer allows the whole system to branch out and reason across multiple paths all at once. And it's all shielded by carbon, tuned by boron, and stabilized by a solid diamond heat base at the bottom to spread out that heat and guide the light.
The source material uses some absolutely fascinating, unique terminology to describe the inner workings of these layers. We see things like whale logic, acting as a structured internal language, and flower of life geometry ensuring perfectly ordered routing. And look, these aren't just poetic names, they are absolutely crucial structural elements. Without this ordered routing and those noise-canceling slate layers we just talked about, the multipath fractal branching would literally just collapse into random confusion. Instead, these structures maintain perfect, high-speed optical control.
All right, Section 3, decoding the massive numbers, translating the specs.
So we know the anatomy, but how powerful is this thing, really? Let's zoom out and look at the numerical scale because it is staggering. 1 quadrillion, that is 10 to the 15th power. According to the blueprint, this is the top-end number of useful actions per second for just a single active zone. An active zone is just one tiny local patch in the chip where information enters, turns into light, gets shaped by that graphene, and returns as a decision. One tiny patch turning information into light-speed decisions a quadrillion times a second. Just let that sink in.
Now, let's step it up to the whole module. 1 quintillion, 10 to the 18th power. This represents the aggressively optimized throughput of all those local active zones stacked together. It's not just one fast layer. It's a fully coordinated machine where thousands of photonic regions are firing and working together as a unified body to achieve ultra-low latency.
But this is the number that truly drops the jaw. A 1 followed by 51 zeros, 10 to the 51st power. This almost incomprehensible number is the potential size of the core's internal state space as fractal depth increases.
So the crucial point is that this massive state space is not a clock speed. It is literally a universe of possible thoughts. It represents the astronomical number of distinct internal arrangements, memory states, branch choices, and routes the system can explore simultaneously while solving a single problem. It holds a gigantic number of possibilities alive all at once.
Let's bring this down to earth in Section 4. Real-world capabilities. What it can actually do.
Which naturally leads us to a very practical question. What does a light brain with these kinds of specs actually achieve in our daily lives? And this brilliantly illustrates exactly that. As a fast analyzer and signal router, it takes varied inputs, things like video, audio, or raw thermal sensor streams. It then applies actions, like pattern recognition, and spits out highly structured intelligence. So it doesn't just give you raw data back. It gives you organized visual analysis, performance graphs, and even complete electronic or material blueprints based on your design parameters.
The specific abilities detailed in the source are just extraordinary. It doesn't just store files like a standard hard drive, it actually stores behavioral memory and routing memory. It remembers which inputs led to good outcomes. And because it indexes by meaning rather than just a simple file name, well, in principle, it could retrieve a lifetime of your conversations or instantly pull up all your writings and drafts from past years just based on the context of what you're currently asking. It can even propose entirely new material compositions by simulating and ranking which structures might behave best under certain heat or light conditions. It's essentially mapping your entire digital life and actively reasoning through it.
Let's move on and see how this builds into a dynamic, step-by-step problem-solving process on the fly. First, the core uses predictive routing to guess the best path for data before a problem is even finished, which saves massive amounts of effort. Second, because of that physical sandwich stack we looked at, it can handle multiple problems at once by assigning different layers to entirely different tasks. And third, it features physical self-correction. If one fractal path hits a dead end, no problem. The layered system simply tries another route instantly, making it vastly more resilient than a rigid single-route chip.
Which brings us to our final part. Section 5. A new physical intelligence. The structure is the answer.
This right here brings us to the ultimate paradigm shift this entire explainer covers. We're talking about a move entirely away from passive hardware. The source material perfectly encapsulates this shift with a great quote, structured so the shape of the material becomes part of the answer. Think about that. The diamond, the slate, the mica, the graphene, they aren't just protective casings wrapped around the logic, they are the logic. The materials themselves actually participate in the computation and memory.
To summarize the core takeaways from the blueprint, this upgrade represents a massive, three-pronged leap in capability. First, it computes faster, because light-based components have incredibly low latency. Second, it computes in parallel, because the stacked regions work on different parts of a problem simultaneously. And finally, and most importantly, it computes structurally, utilizing the actual geometry of its physical materials to reason.
This leaves us with a truly profound realization about the future of our technology. We are looking at the absolute dawn of light-powered, self-organizing physical intelligence. So, I'll leave you with this thought. When our devices don't just calculate, but physically reason at the speed of light, exploring a literal universe of thoughts in a fraction of a second, what will we ask them to design first? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.